Good afternoon. Good to see the last one. My name is Zichong Chen. I'm made by the Tim and Dylan. When I was a very young little kid, I grew up with my grandparents in the east part of China. It's a agriculture dominated area. We grow a lot of sweet potato, peanuts, and a little bit corn. And most of the time, I was playing with myself in the farmland. I guess by that time, I grew the interest in the agriculture. And when I grew up and older, I continue my interest in the agriculture and come here, the U.S. Corn Belt, to continue my interest. I have a great interest in the biophysical mechanisms of the greenhouse gas between the surface and the atmosphere. And in particular, I am interested in the surface atmosphere exchange of nitrous oxide, carbon CO2, and the water vapor within the agriculture system, especially the U.S. Corn Belt. We know that each year for the U.S. Corn Belt, there's a lot of nitrogen is input into this area. That means a lot of greenhouse gas, nitrous oxide, will be emitted. So that's Kelly to give the introduction of the inverse modeling. And I also use the inverse modeling to give a regional constraint of the nitrous N2O budget. And also I want to partition them. The left figure shows based on the tall tower subsoil sample, we make a very high resolution measurement of the N2O concentration. And the left figure shows the seasonal shift of the footprint. It generally shows us how much or how large the area that will influence and contribute to our tall tower measurement. And the right figure shows a comparison between our method and the top-down with the bottom-up method. As Kelly said there, talking about the emission factor, our method, and which agree pretty good with the other tall tower measurement, with a top-down constraint. It's much larger than the bottom-up method. And yeah, this is the work I have been done, and I'll give a little bit introduction of the work I'm been doing. And currently, I'm trying to evaluating the performance of N2O production using a community crop model, COM, and also based on the tall tower measurement. I try to use that, based on that, to optimize the community model, the service model, and try to reach a good fit. And then, based on this optimization, I want to set a future run based on the RCP 2.6 and 8.5, give the best conditions and water conditions to see how the temperature change, precipitation change will influence the future change in the climate. It's at the very beginning stage. Currently, I'm struggling, to be honest. Yeah, that's what I have today. Thank you. Yep.
So you said, I think it was the last slide of the slide. Yeah, that one. So the image on the left, that you said is the footprint of the tall tower measurement?
Yes, the concentration footprint.
So how is that determined?
Oh, yes. We use our transport model. It's a backward transport model. For example, you have the location of the tall tower, and you know the height, you make measurement, it's 100 meters, and we set the transport model is called field, it's backward. Generally, you release let's say 1,000 or 500 particles from the tall tower at the height of 100 meters, and it goes backward 7 days based on the meteorological conditions like the wind, the boundary layer conditions. If you backward 7 days, and you can tell the strength of each region or each area, how much it will contribute to the tall tower. That's generally how we do that.